Welcome to a molecular spectroscopy of physical chemist perspective week one live session. I am Orko Prabhu Chaudhary. I am a PMRF at chemistry department at IIT Bombay. So I will be helping you with you. I will be a teaching assistant in this course and I'll be helping with you to solve numerical problems as well as we will discuss some of the uh, problems or understanding whatever problems you have in understanding the topics is taught by Professor Datta in the NPTEL course. And today is the week one session. So we'll have um, at least 12 and maybe one more extra session, that is 13 sessions. And these sessions will be on mostly on Tuesday, 6 to 8 p.m. So, the objective of these sessions are solution of your weekly assignments and obviously to clear your doubts. So, whoever suppose today no one has joined yet. So, this session will be recorded and will be available on the YouTube. So you can always go to the link. Link will be provided to you. Link and YouTube link and the PDF or notes materials will be provided to you by the NPTEL team. Now I will share with them. And so today we will start our session. So today I want to start with, so as it is a molecular spectroscopy course, so today I want to start with the electromagnetic spectrum, right? So this is very important for spectroscopy. So in electromagnetic spectrum, as you can see, so in the scale is not to the scale, but what you can see is, let me use my pointer. So as you can see, the energy of the waves, so this is a long wavelength, short wavelength. So long wavelength means radio waves, very long wavelengths, right? Then microscope, then infrared, uh, infrared region is there, whose wavelength is longer than the visible wavelength. So the visible wavelength actually, if you see, if you want to discuss in maybe maybe here, as you can see, so it will be something around 750 nanometer to 350 nanometer, right? This is the range of an um, visible light. And then again, obviously, the ultraviolet portion is there, and X-ray and gamma ray. As you can see, this can be obviously this can be summarized with this, that energy is hc by lambda, right? Or maybe h nu. H is Planck constant. C is obviously the velocity of light, and lambda is the wavelength, and nu is the frequency. So as you can see, the frequency is increasing and lambda is decreasing, right? So obviously your nu varies as 1 by lambda. So these are the things are very important. So I thought that I should start from this. And also you can see that as the lambda decreases, nu increases, so energy also increases, right? So, okay. So with this, I will have some basic questions to start with again. So the first question is that the different types of energies associated with the molecule are. So the options given are electronic energy, vibrational energy, rotational energy, or D, all of them mentioned. So obviously there is no one to answer this question right now. So let me give you the answer. Obviously the answer is D, all of them mentioned. Okay, because this electronic energy depends on the energy difference between the electronic states. Vibrational energy comes when we are discussing the vibrational levels, and again rotational energy comes when we are discussing the rotational levels. And for your information, our question is there in the week zero assignment. Obviously, the electronic energy is greater than the vibrational energy, and vibrational energy is greater than the rotational energy, because our electronic state is consist of several vibrational levels. So if So this is an electronic level. Suppose I'm naming it as uh, is 0, which is a ground singlet state. So these actually consist of various vibrational energy. Okay, so these consist of several vibrational energies. So, and each vibrational energy also consists of several um, rotational energy levels. So if you can think like this, so as you can see the electronic states, suppose I have another electronic state, suppose I am writing this in black is 0 ground state, which is black means the electronic state, right? So this is 0 and similarly there will be something S1, okay? And that energy is increasing this way. So as you can see the energy, so this energy is electronic energy and difference between each vibrational rate levels are vibrational energy and rotational energy comes between this electronic, these green levels, right, which are rotational levels. Okay, now the second question is during the motion, if the center of gravity of a molecule changes, then the molecule possesses the electronic energy, B rotational energy, C translational energy, or D vibrational energy. So the answer is actually translational energy. And you will come to know that all of these energies are actually, these are not continuous. These are actually, if you can say, these are these can be obtained and also by the use of quantum mechanics you will be able to show that uh, these are not continuous, but translational energy is a continuous energy. Okay. Okay, so from here we'll go to week 0 assignment, which is given in the NPTEL portal, and we'll try to solve them. I'll not discuss the week 1 and week 2 assignment today because the due date is still remain on 7th February. So until 7th February, I will not discuss those questions. I'll try to solve similar kind of questions on the next day and also discuss the week 2 lectures today. After this week 0 assignment, solving of this week 0 assignment, we will discuss a few topics which was discussed by Professor Datta in the week 1 lecture of. So let's first start with this week 0 assignment, question number 1. So the question number 1 says that any wavelength can be written as a linear combination of eigenvectors, eigenvalues, eigenfunction, and operators. So the answer is actually your eigenfunctions, right? Because a function can be written as a sum of linear combination of eigenfunction, and it is an eigenfunction of a particular operator, right? Okay. Suppose mostly in this case energy, when we are discussing this molecular spectroscopy, so the operator is actually the energy, right? The total energy. Now, second, the correct order of different types of energies. I already discussed this, that the electronic levels have higher energy gap than the vibrational, than the rotational, and obviously then translational is there as a continuous source. So this is the right answer. Now, third question. The region of electromagnetic spectrum or radiomagnetic resonance is. So I believe who is dealing this subject for the first time, it will be unknown to him or her. But actually, the NMR spectroscopy, the nuclear magnetic resonance, this is going to be taught at the end of this course. Right? So you will get to know what is this. But for now, let me give you the answer. The region of actually the electromagnetic spectrum for nuclear magnetic resonance is actually radio frequency. And as you have seen from the first diagram I have shown to you of electromagnetic spectrum, the radio frequencies actually have very high wavelength, right? The lambda is very high, and as a result, the energy is very less, right? And what about this other three? What is microwave region or microwave electromagnetic microwave region? What does this stands for, or which spectroscopy is done in this region? Microwave. Microwave is done for rotational spectroscopy. So this is the I think week two lecture. Week two. In week two, this will be taught. And infrared actually deals with the vibrational vibrational spectroscopy, and UV rays and other. This will UV or visible, that will actually comes with this electronic state. You will come to know electronic spectroscopy. So the question number four, the bond lengths of a homonuclear diatomic molecules can be determined with the help of both rotational and vibrational spectroscopy, rotational Raman spectroscopy, rotational Raman and electronic spectroscopy, and fourth option is vibrational and electronic spectroscopy. So whenever this bond length is being discussed, obviously in week two you will get to know more about this, but uh, whoever also see for me also whenever I know this, but still I will make mistake. The homonuclear diatomic and bond length, whenever the question of bond length come into picture, we always think about rotational spectroscopy, right? But because there is this B is there, B one constant is there, we'll come to know in the second week. Obviously, I will not go into the deep, but whenever we are discussing a homonuclear diatom, then the actually the dipole moment is zero. And for dipole moment, whenever dipole moment is zero, we can't really work with the rotational spectroscopy, but we can do rotational Raman. So the answer is actually going to be rotational Raman and electronic spectroscopy. So the third option is correct, not the other. Okay. Now question number five. Question number five says that the transition zone for Raman spectra is between vibrational and rotational levels, between electronic levels, between magnetic levels of nuclei, or between the magnetic levels of unpaired electrons. The answer is actually vibrational and rotational levels. I know you might be thinking that why these questions are given if it is not taught yet. The questions are given to familiarize you with the topics we are going to read in the further weeks. Okay, this is the main motivation behind these questions. It is not to test your knowledge, but to give you an idea, as these are the topics we are going to deal with. Okay. Now, question number six. Select the incorrect statement from the following option. First question, first, what is the statement given? That emission spectrum results when an electron in the atom undergoes a transition from excited state to ground state. This is actually a correct statement. Then the second statement, in the emission spectrum, transition takes place from the emission of a photon of energy Hν. This is also correct. Now, third option, third statement, in the emission spectrum, transition takes place with the absorption of a photon of energy Hν. And fourth option is all of the mentioned. Actually, as you can see, the first two statements are correct and the third one is incorrect. So we need to select this. We need to select this. So this is the incorrect statement upon all these three, you can say. Now, what is question number seven? Question number seven is, which of the following statement is true regarding the photoelectric experiment? The photoelectric experiment was first done by Einstein, right? The photoelectric effect. So he gave the theory behind that and got Nobel Prize. And so the question says that which of the following statement is true? So we need to find out the correct statement. So the first statement is the stopping potential increases with the increase in the intensity of incident light. So it is saying the work function actually increase with the intensity of the incident light. So work function is a constant, right? So this is a incorrect statement. What about the second statement? The photocurrent increases with the intensity of light. What about the third one? The photocurrent increases with the increase of frequency. Frequency is increasing, then obviously your energy will increase. And what about the fourth one? The photocurrent increases with the increasing wavelength. If the wavelength is increasing, then the energy is decreasing, right? But you see, what will happen if you increase the intensity of light? Intensity of light won't increase the intensity of light don't increase the energy, but it increase the number of emitted electrons, right? It will increase the emitting electrons. So the photocurrent will increase actually due to the intensity by the increase with the intensity of light. What will happen if we increase the frequency? If we increase the frequency, then suppose earlier one electron was being emitted. When we increase the frequency, the energy of that emitted electron is high. So work function is constant, and the kinetic energy of this emitted electron will be higher than the previous case. But current is actually what? The path of current is the opposite of the path of the electrons, right? So if you increase the number of electrons, emitting electrons, then you will increase the photocurrent. So the correct answer is the photocurrent will increase with the intensity of light. Okay. So now question number 8. So question number 8 is saying that concerning the nucleus spin, which of the following is true? First question, spin is due to the rotation of the nucleus about its axis. It is actually wrong because spin is actually not a concept of, you can say, it is a quantum mechanical phenomena actually, be it electronic spin or nuclear spin. And what about the protons have spin but neutron do not? This is not correct. The third option is spin can only have integer or half integer values. This is actually correct. And another name of spin is Precession. This is not correct. This is actually not correct. Okay. And now we will discuss the week one lectures, some few topics. Okay. Uh, As we will discuss the topics, we will solve some numerical problems also. So the first lecture actually deals with the frequency domain spectroscopy, right? Domain spectroscopy. Mostly, Sir has taught about uh, electronics, electronic spectra, which are like electronic spectroscopy, mostly absorption and emission spectroscopy, right? So this absorption and emission can be both, right? Emission can be what I both by I said fluorescence, radiative transition between the same state of same multiplicity, and phosphorescence. Phosphorescence is the phosphorescence, the radiative transition between the state with the different spin multiplicity. Mostly it is known as the triplet T1 to S0. But any spin multiplicity, different spin multiplicity, a radiative transition will be known as phosphorescence, and similar multiplicity of the states is radiative transition is fluorescence. Obviously, absorbance you know, and this has been also discussed that from the absorption it was taught about the Beer-Lambert law, right? Beer-Lambert law, which actually says your absorbance, which is actually log of I0 by IT, which is actually a doesn't have any unit, right? It is epsilon CL. Epsilon is molar extinction coefficient. It has a unit, right? It has a unit mole inverse centimeter inverse, right? Then this is your concentration, obviously, which has a unit of mole, and this is your path length, the optical path length. Most of the time, this is the length of a cuvette or the optical instrument, the holder you are using. This is that, and the unit is obviously most of the time we write it in centimeter. That's why this is molar coefficient, extinction coefficient has a unit of mole inverse centimeter inverse. So for fluorescence spectroscopy, actually, SAR has also shown that what does absorbance of 1 or absorbance of 5 means. He has also shown that absorbance of 5 actually means that it is actually a opaque, right? It is actually opaque. Now, why it is opaque? Because the epsilon, the concentration is very high, right? Okay. Now, so light cannot pass through. Okay. Now I won't go that side. I will now discuss that for fluorescence, actually we use a very dilute sample because of some of the things called inner filter effects. There are inner filter effects like fluorescence. To avoid inner filter effects, use uh, dilute solution. How much dilute? The dilution should be less than 0.1. The absorbance should be less than 0.1. So even in some cases which are very highly emissive samples, in that case, it can be even lesser than that. It should be. So I will not go into the deep of inner filter effect. That is a part of a different course. But now let me discuss the instrumentation of this absorption spectrophotometer. The image you are seeing here, the image here you can see is actually an example of a spectrophotometer made by Jasco V530. I'll write the model number here. So this is actually is in your lab and we have opened it to show you. The Jasco is the company name, Jasco V530. So so this is an example of double beam spectrophotometer. So I'll write that uh, instrumentation station of a double beam spectrophotometer. Okay, so the example you can see is this. So I'll write down that what are the things there. First, obviously there is a lamp, right? So this is the lamp. The light will come. Obviously there is a monochromator. I'll write uh, monochromator here. Today we will discuss what is a monochromator deeply. So this is an actually a wavelength selector, right? Right? And then there will be a dichroic beam splitter, 50-50, 50-50 beam splitter. One part will go to your one cuvette and another will be reflected. One is transmitted, another is here is another mirror will be reflected here, and there will be another cuvette, and then there is a detector, then there is a detector. Suppose this is detector 1. uh, this is detector 1, this is detector 2. So here will be your sample, and this is a mirror, and this is your reference. So here your IT will be measured, and here your I0 will be measured, and then it will be fed to a computer, suppose, and you will get the spectral from here. The spectra will look like something like this, right? So here let me show you how this works. So this is interesting, right? You can see what is the part here. So this is actually the lamp part, lamp. So this is an deuterium lamp. Okay, this is an deuterium lamp which actually emits in the UV region. So this is an deuterium lamp D2, and this is an tungsten lamp. Tungsten lamp. So there are two lamps, and there is a mirror. So this part emit the UV range, and this is for visible light source. So the mirror will automatically change. Automatically change means the change will be set by the obviously the computer, whatever wavelength we are selecting to excite with. So this will reflect the UV, and this will reflect the visible part depending on the angle of this. Okay. Now this part actually you can see, you may not be able to see. Let me use an uh, pointer. So this is your deuterium lamp, this is tungsten lamp. Depending upon the excitation range, the mirror will change its position, and light will be that particular excitation light will be he will come from here. So maybe I'll use another pen. Which color? Maybe green color. Suppose the light will come from here. Okay. So there is a filter wheel is there. You can use different kind of filters of your choice, or maybe suppose it is empty. So there is a slit, and it will fall into, actually this is your a concave mirror. So this is not only just a mirror, this is a monochromator. So it has several gratings. We'll discuss that. We'll discuss that in maybe 10 to 15 minutes of time. But believe me, the monochromator is an instrument which is a wavelength selector. Depending on the incident wavelength and the diffraction wavelength, the wavelength can be varied. Okay. So white, suppose a light, tungsten light, this white light is falling into this, and that will be diffracted at different angles depending on the incident light and obviously the grating size and all. And uh, using this screw system, this screw will uh, also let this mirror to move, rotate. So the whatever will be the choice of light we have, so the monochromata that will come from here. Okay, now suppose okay, let me use maybe I will erase this, the green color. I will take a um, white color, that would be more. Suppose the white light is falling here, and then suppose I am currently working with a green, exciting it with a green excitation source. So green will be, acha, so sorry for that. From this monochromata, the green part is being selected, and this is the exit slit. It will fall into this uh, mirror. Okay. Now, from this mirror, what will happen? It will fall into this mirror. But here is something that 50-50 if beam splitter is there. So it will transmit 50% and it will reflect 50%. Some will come here and some will come here. So this is the 50-50 beam splitter, right? And then these are the mirror systems. So now 50% will go to your sample and 50% will go to your reference. And then suppose the photodiodes are kept here, as you can see the some circuit board you can see here is photodiode 1 and photodiode 2, which will actually detect the photons and intensity of the transmitted light, and it will fade to the computer system, the whatever electronic system is there, and by computer you will get this kind of spectrum, right? I hope this is clear to you. And next, I'm going to discuss another kind of. So, in this kind of uh, instrumentation, you may find one problem, that the detectors you are using, it may not have similar sensitivity. So then the problem will come that you are not detecting properly. So for that, to avoid that problem in double beam spectrophotometer, and nowadays another kind of instrumentation is being used, that is almost similar technique. I will try to copy paste that in the next slide maybe. Um, Almost all the things will come. Okay, I'll draw once here. No one has joined. Okay, no problem. You can see this thing in the online, right? So, so to avoid the sensitivity issue for current detectors, we can work with only one detector. So how it will look like? Similar. The the source is there, the lamp. Light will come. There will be monochromator, right? The work of a monochromator is to separate the polychromatic light and give you a single wavelength. Then I will not write here, but suppose earlier what do we have? We have this system, right? Here is your sample, and we had our reference. Actually, instead of a beam splitter, we will use a spinning disk, which will be monitored by the, obviously, which will be connected to the means which will be monitored by the computer system, which will have three different parts. One part will be a mirror. So one will be mirror, one will be transmitted. Okay, so mirror, let me write it like this. One will be opaque. Opaque means light won't pass through. Okay, this kind of wheel disc system will use, and uh, again the rest of the thing is similar. We'll have a mirror here when the light will come to the reference. We'll have a mirror here, and we'll have a similar kind of disc here. These two discs will be controlled by the computer, obviously, and these two have a specific sync. I will tell you what is this. So obviously one will be mirror, one will be opaque like this. I think this is not discussed in the class, so you may find it interesting. And obviously one will be mirror, right? And I hope you can understand what I'm trying to write. Okay, and then there will be only one detector, and obviously there is your computer and all. Okay, so these two disks will be in sync. How? See, when the monochromator, when the disk will be in this, so monochromator, one monochromatic light is coming through of some intensity. It is, suppose the disk, this disk in this condition, so that it is hitting the mirror portion, so light will be reflected and it will fall into the reference, and this disk will be in transparent condition. Okay, so suppose I am writing it uh, disk 1 and disk 2. It will be in sync how 1 disk. So the spelling of disk is, what am I doing? How can I write this? When the disk 1 is in mirror, then this will be in transparent. Transparent. When this is transparent, transparent, this one will be transparent, then the intensity of light will go through the sample, it will not come here. So this should be mirror, so it will reflect the light to detector, so this will be mirror. And when this is opaque, this will be opaque. I'll tell you what is the function. So here the detector will, the first case the detector will get I0, the second case detector will get IT, and third case it will detect I thermal. So So when there is no photons involved, still there are some counts. So these intensity is due to the thermal noise actually. So this can be also calculated when both are in opaque. Then whatever intensity is reaching the detector, that is the thermal detector, a thermal noise. So as you can see now, your absorbance A is formula is actually log I0 plus I TH, this thermal noise, and your IT plus I thermal. So these will also be calculated and you will get a better absorbance signal when the sensitivity issue is also solved and the say issue of thermal problem or thermal noise is also solved, right? And so these are the basic instrumentation of a double beam absorption spectrophotometer. And next, let me discuss an instrumentation for um, instrumentation for fluorescence fluorescence measurement. Or you can not fluorescence, but also we can write emission, right? Because most of the time we measure the fluorescence, but the phosphorescence measurement can also be done. But for phosphorescence measurement, there is something else is also involved, which we beyond the discussion is beyond the topic right now what we are discussion. But mostly emission by I mean fluorescence. So there will obviously there is again the lamp is there. Now this lamp intensity is very high, very high intensity lamp is required. Mostly this is a xenon lamp. And I told you by showing the image for absorption spectroscopy, one deuterium and one tungsten lamp is used. So xenon lamp has can emit from UV to visible. Still, we don't use that in the absorption photometer. This is an interesting question. You try to answer it. Why we why don't we use why xenon lamp not used for absorption spectroscopy? Try to answer this. Huh? This is an open question to you. Those who are seeing this video, you can write in the comment section, or you can obviously who are joining tomorrow. Oh, the tomorrow means the next Tuesday session. Please try to answer this. So xenon lamp. Let me give you a hint. The xenon lamp has a very high power. So the lamp will polychromatic light will come again. We need a monochromatic excitation, so a monochromator is there. It will fall into your cuvette where our sample is there. And actually to avoid the stray light means the light of this whatever transmitted light. To avoid that, we collect it in a 90-degree fashion, or uh, 90-degree fashion. And here is another monochromator, and then wavelength selector, then there is our detector. This is a very simplified version I am showing you. suppose here we are generally what we do, we say that excite our sample with some lambda excitation, and then what is happening that your emission has a again will be polychromatic, right? It has suppose it has a band and it has multiple wavelengths inside it. So, during your emission measurement, your lambda excitation is fixed, and this so this is emission monochromator, this is excitation monochromator. So excitation monochromator is fixed, but lambda emission is varied. So this is varied. Emission monochromator is varied, and then you will get something emission spectra. Okay, and you will also come to know about excitation spectra. Excitation spectra. I am not discussing it right now. At that point of time, actually, this lambda emission is fixed and your lambda excitation is varied. Not lambda excitation, but this monochromator is being varied. Okay, that is what I am trying to say. Okay, I'll not go deep into that. And another concept, obviously, to quantify the let me use another color maybe quantification of fluorescence is mostly done by the quantum field, right? It is taught. Some portion is taught. Some question I think are there in the week one assignment. I will discuss some of the question next day. Generally, the quantum field is given by phi, uh, small phi, f, or you can write it capital. It is actually number of photon emitted by the number of photon absorbed, which is nothing but equals to actually your intensity I, emission intensity divided by intensity of absorbed light. We can, Sir has shown, I guess, the intensity of emission by, I guess, I0, the incident light, 1 minus 10 to the power minus absorbance. So this is one process, and obviously we calculate it with a reference of a. We can calculate quantum field by two methods. One is absolute method, and another is reference method. Uh, the reference method, we take a standard dye and calculate the and take the spectra, and the for the standard dye the quantum field is already known, and we use a formula. The formula is already being taught in the lecture. Please refer to the lectures. I'm not writing it right now. We'll solve some numerical problems tomorrow. Tomorrow means the next session. But another option is that um, absolute meter using an integrating sphere. Uh, if time permits, I will discuss this maybe on tomorrow the next session. So now what I am going to do, I am going to jump from all of this, and I will not jump, but I will actually go back to this monochromator section. What is actually a monochromator? So this part, whatever I am going to discuss is from Principles of Instrumental Analysis, this book, 7th edition by Skook, Holler, and Crouch. As you can see, so you can refer to this book. So whatever I'm showing you here is a monochromator. Let me. So this is an suppose this is a typical monochromata. I will show you what these are, discuss point by point. This is suppose a monochromata. A entrance slit is there. Suppose polychromatic light means suppose uh, a white light or polychromatic light is falling through the entrance slit. There is a concave mirror. Okay, so these the job of this concave mirror are to collimate the beams. Collimate, they are collimating onto these refraction gratings. So this grating actually have a finite number of groups at a equidistance. Okay, so falling onto these groups actually the this is where the all these monochromata, this is a main part of a monochromata, the grating depends on the diffraction angle. Two wavelengths will be generated. Okay, so here as you can see the wavelength which is actually shorter, that is lambda 2 here, let me write lambda 1 greater than lambda 2, which is shorter, that is actually has a sharper reflection, you can say. Okay, so this is actually lambda 2, this one, and this is lambda 1. So and after they were again comes to this concave mirror and they are focused to a exit slit, and depends on the slit width we are going to get lambda 2 or lambda 1. So this is the fundamental of a monochromata. Okay, now from there let me show you the gratings here. Okay, so let suppose we are zooming onto this portion. Let me use another color. So here we are actually they are saying we are using a monochromatic beam. Okay, so monochromatic beam, three such beams are falling onto this monochromata at an angle, incident angle I, with a normal to the grating normal. So this is grating normal. Normal means perpendicular to the x-axis, suppose. Okay, so this is falling onto an angle I. So the first beam is coming to A and getting reflected. Second beam is coming to B and then reflected. And also third one is falling here and getting reflected. But the angle is I for 1, 2, and 3, and angle is reflection is R for 1, 2, and 3, and they are collimated again. Right? Now the distance between each groups, you can say, or the distance between A and B is given as B. So this is the distance between two groups. Okay. Now see what they are discussing here. So in figure 721, parallel beams of monochromatic radiation 1 and 2 shown striking the grating at an incident angle I to grating normal. We have discussed this. Then maximum constructive interference is shown as occurring at the reflected angle R. So they are saying that at R, the maximum constructive interference is being happening, occurring. Now they are saying that beam 2 actually is traveling much more path length than the than the first beam, right? Obviously, how much difference is there? As you can see, the difference is the BC and a CB and BD, right? It is saying there that the path difference is equals to CB plus BD. So they are saying for constructive interference to occur, the difference must be equal to n lambda. Okay, so the difference must be n lambda, where n is a small whole number called the diffraction order, as you already heard of first order diffraction or second order diffraction, right? So this n is the diffraction order, and n lambda should be equal to CB plus BD, the path difference, to be to get so that we can get a constructive interference. Now what they're trying to say that what is the value of CB and BD. So to actually see that, let me use my pen. So they are actually here. They are. I will try to draw here. They are actually considering B A. The distance is D. This angle, this triangle, and there is another triangle D. So from these two triangles, they are trying to get what is the value of CB and BD. So if you actually see the geometry, you are going to see that angle CAB is going to be also I, and angle DAB is going to be R. I will show you how this is done. Even if it will take time, I will show you. Please be patient here and look at what I am trying to say. So I might confuse you, but please also see that this angle is I. Whatever I am going to show you the ray, this is for I. This is I. Okay. Now we are going to only now focus on this part, this triangle ACB. Huh? So we want to know what is the angle CAB. We know that this angle, so for suppose for triangle ABC, we know the angle ACB is 90 degree. Okay. And this angle, whatever going to draw, this is also 90 degree, right? And suppose I'm going to, so this angle is also 90 degree, and this angle is I, this angle. Okay. This angle is I. So what is this angle? What is this? This is 90 degree minus I. This is 90 degree minus I. Okay. So if this is 90 degree minus I, and this is very so I will erase some part so that it is clear. So this angle is 90 degree. This angle is 90 degree minus I. Okay, because this is I, this is 90, so this part is remained, right? So that is 90 minus I. So if this is 90 minus I, what about this angle? This means suppose I am pointing out this point is M. What about, so again we are going to another triangle. Where is my cursor? So suppose I am discussing triangle AMC. There we know MAC is 90 degree minus I. Angle ACM is 90 degree. Then what about angle AMC? That would be 180 degree minus these angles, which is 90 degree minus 90 degree plus I. So your this is actually I. Your angle AMC is also I. Oh, wait, a minute. Joint. No, stay in the call. It will come back. Okay. So your this angle is also I. Okay. Now I'll erase this part. I will keep this part. Okay. And this I can't remove. So I'll write it here. So this angle is I. Now suppose if you are considering another triangle AMB, then what you got? You got your MAB angle is 90 degree again, because why? Because this is normal, grating normal with respect to AB. So that is 90 degree MAB. Then you know your angle AMB is I, right? So what about your angle ABM, or suppose ABC, that is your 180 degree minus 90 degree minus I, that is 90 degree minus I. So this is also 90 degree minus I. Okay. Now we will come back to triangle ABC. We already got ACB is 90 degree. Now we got ABC, which is 90 degree minus I. Similarly, we will be able to show then CAB is obviously for, now we know this is 90 degree. This is 90 degree minus I. So CAB is 180 degree minus 90 degree plus I minus 90 degree, which is I. So this angle is also I. Okay. So now when we know that this angle is I, CAB, and we know this is D, so for this we know, for this angle ABC, we know that uh, um, if you take a sin I is your uh, perpendicular by hypotenuse, right, which is CB by AB. So your CB is, you don't know, and this is D, right? This is given the distance between each grating. So then your CB is D sin I, and that is what they have also written here. Okay, so so it was a little difficult for first time to understand why the angle is I. So that's why I just I helped you with that. Similarly, you know this angle is R, the reflected angle is R. So from there, you will be able to show that, suppose I am going to change my color to green. So from there, you will be able to show this angle is actually R. Okay. Um, should I'm thinking that if I should show this to you, or is it you will be able to solve this by yourself? Maybe I will show you why BD is D sin R. So I'll just copy paste this whole slide, and I will delete maybe this thing for now and only discuss this R part. So for now, what we already know, I'll again draw this once again, that we have two triangles. This is C, this is D. We have shown you this angle is I, and currently we are going to show you that this angle is R. Okay, so this is the angle R, and as you can see, this is a perpendicular angle, right? Because this is perpendicular on BD, this line. So this is also perpendicular on that, and the angle between this, if we are going to consider this angle, so angle BDA is also 90 degree, and this is also 90 degree. And if this is R, then suppose we are considering now this point as N, and let us suppose we have A, not that point. Suppose this point is N. So for the triangle AND, what do we have? So we are going to have angle ADN as 90 degree. Obviously, this angle is also 90 degree. This angle is 90 degree minus R. Which angle? NAD is 90 degree minus R. So what about this angle? AND. That is R, right? So this angle is going to be R. If this is R, now mm, do you really want that? Now suppose we consider the triangle ANB. For there we know that angle NAB is 90 degree. Now angle BAN is R. So what about angle ABN? ABN or angle ABD? Same, right? ABN or ABD is going to be 180 degree minus 90 degree minus R. So that is 90 degree minus R. So this whole angle is 90 degree minus R. And we already know what angle ABC is. Angle ABC is 90 degree minus I. So was it even required? No, it was not required. Angle ABC, invoking that angle is not required. I'll erase this. See, I myself getting confused. So this is 90 degree minus R. Then what about angle? So for triangle ABD, we have angle ABD as 90 degree minus R. We have angle ADB as 90 degree. What about then angle DAB? that is 180 degree minus 90 degree plus r minus 90 degree, which is r. So this angle we got as r, right? That is what we are trying to find out. So this is r. Then again, by similar analogy, if this is r, this is, so for triangle, this triangle, sine r is BD by AB, which is D, then your BD is D sine R. Okay, that is how you can get this. And from here, you can see that if you fall into this n lambda is equal to CB plus BD for a constructive interference, you will get this relationship. The relationship states that n lambda is equals to D into sine I plus sine R. So this is one of the important uh, relationship which we will use to calculate, or cannot calculate, but solve a numerical problem which is coming in the next slide. Okay, okay, let us do that. So the numerical problem says that, and so the kind of gratings what we are seeing here, so that is known as echelet. I'm not sure if I am pronouncing it correctly. Echelon type grating. So for uh, similar kind of grating that contains 1450 blazes per millimeter. So it contains 1450 blazes or groups per millimeter was irradiated with a polychromatic beam at an incident angle of 48 degree. So So incident angle, that is I, is 48 degree to the grating normal. Calculate the wavelength of radiation that would appear at an angle of reflection plus 20, plus 10 degree and 0 degree. So your sin I is, we know the equation, right? We know the equation that n lambda is equals to d sin I plus sin r, right? This is the equation, d sin I plus sin r. Now, so what is your sin I is going to be? If I need to calculate without a calculator, let me in my mobile calculator. So sin 48 going to be 0.743. Okay, and what do I need to calculate? Calculate the wavelength. So the wavelength is going to be d by n. Sin I now know 0.743. Now sin R. Sin R is your reflected angle, which is given plus 20, plus 10, and 0. So for plus 20 degree, what we are going to get, lambda is equals to, and d. What is the d? The distance between groups or uh, or blazes. Here you can see groups or blazes, or let us say like that, which is going to be, so at 1 millimeter there are 1450 blazes. So this distance between each blazes are 1 millimeter by 1450, right? Which does mean is 10 to the power 3 meter minus 3 meter by 1450, and the value is actually value is 689.7 nanometer. This is the distance between each groups. So I'll write it here. Instead of 689.7 nanometer, I will write divided by the order of the diffraction, then 0.743. And what about sine R? If sine is 20 degree, 0.342. So this is coming to be, lambda is coming to be 748 by zero point 0.4 by n when the it is plus 20. What about plus 10 degree? And the lambda will be same, that 689.7 nanometer. So this is coming in nanometer. So I will directly write the answer is going to be coming as 632.3 nanometer. And what about 0 degree? It will be 512.5 by n nanometer. Now see, depending on the diffraction order, you are going to get first order. If it is n equals to 1, then you are going to get 748.4 for plus 20 degree reflection. It is a second order, then you are going to half of that. If it is a third order, then it is going to be like that. But always remember, the intensity of the first order diffraction is always very, very higher than the second order and then the third order. So I have a table for the same. You can see the values, the lambda, how this is going to be lambda 1, lambda 2, lambda 3. Sorry, n equals to 1, n equals to 2, n equals to 3 for different angles. As you can see, we have got almost the similar results for n equals to 1, right? 748, 632, 513, right? So I hope you will be able to solve this kind of numerical problem, right? Okay. Now, before solving that particular problem, we will discuss we will solve another numerical problem. But before that, we will discuss another concept of monochromator. Okay. So I will again copy paste this and will paste it here. Here also I will delete the writings. So from here, what we already got, we got that your n lambda is going to be d sin I plus sin I. Okay. Now there is a concept of dispersion. Dispersion of grating monochromator. Monochromator can be different types. So currently we are discussing a particular type of monochromator where grating is used. And this is mostly used nowadays. That is why we are discussing this particular one only. So what is dispersion? Dispersion means the ability of a grating or monochromator to discriminate two different wavelengths. Right? I hope this is clear. So the dispersion means dispersion ability or dispersion of a grating is the ability of a monochroma to discriminate two different wavelengths. Okay, there are two kind of dispersion of a monochromator, which is known as angular and dispersion, and another is linear dispersion. And there is obviously there is some relationship between the angular and linear dispersion. We will discuss that. So what is the angular dispersion? So that is actually given as dr by d lambda. How can we get that? We can get that by differentiating this equation, this first equation, with differentiate with respect to lambda, differentiate the lambda with respect to the angle r, keeping I as constant. Okay, so what we are going to get from here, we are going to get d lambda by, suppose dr is d by n, obviously sine I is constant, that is why it is 0, and sine r is going to be cos r, right, when we differentiate with respect to r. So what do we have here? dr by d lambda. So we will reciprocate it. So we will get something like n by d cos r. So this is the angular dispersion. Okay. So this is known as angular dispersion. So what is linear dispersion? Linear dispersion is given by dy by d lambda. So y is the distance. It can be even this much. It can be even this much. So y is the distance on the focal plane, not uh, not on that. Sorry, I have mentioned there. It is that. Actually, yes. Actually, the y is being changed along these. So y is a variable, and that is on this AB. Okay. So dy by d lambda. So that is that can be that we can write. So dy we can write actually as f dr by d lambda. So where this mirror f is the focal length of the mirror, okay, and dr by d lambda, you already know that is the angular dispersion. So this is the relationship between the linear dispersion, which is also known by capital D. Okay. Okay. Now we already established that what is dr by d lambda, that is f dr by d lambda is n by d cos r. Most of the time we work with the reciprocal of this linear dispersion, which is obviously d by n cos r. And as you can understand, this r, if r is very less, if r is very small, less than the 20 degree, then it is going to be something. So this is going to be a constant, the d dash. So because it will become 1 at very close to the zero angle, and it will be something d by nf. And we can always rewrite the equation. Not here maybe. So this is how we can write what are angular dispersion and what is linear dispersion. Okay. Now we'll move to something known as effective bandwidth. So this effective bandwidth is a concept that this is regarding the resolution. I think Sarah taught the resolution in lecture 3 maybe. Yes, I think in lecture 3, resolution, monochromator, signal to noise ratio, these all the things are being taught. So there, this concept of in the concept of resolution, as you can see, what is resolution? How can we differentiate 2 points, right? Or here, how can we differentiate between two wavelengths? So, so if we can't really, if the exit slit, it will depend on the slits. as well as the number of gratings, all of these, right? The linear dispersion and angular dispersion, these all these factors are responsible for the resolution, what wavelengths we are going to get. So, suppose we are going to get, suppose this is your exit slit, this is the exit slit, and we are currently focusing the monochromator, that mirror is currently focusing lambda 2, then uh, what is going to be the effective bandwidth of this uh, wavelength? So this effective wavelength is nothing but uh, lambda effective, what we are talking about. This is effective bandwidth. This is actually going to be half of this bandwidth when exit and entrance slit are equal. Here it is written, see, illumination of an exit slit by a monochromatic radiation lambda 2 at various monochromator settings, exit and entrance slits are identical here. So currently we are discussing about if lambda delta lambda effective, which is effective bandwidth. How can we relate this? So we already know that linear dispersion of the grating with the mirror is D, which is, now I can write in a finite term, delta lambda by delta y, which is change in the finite width, right? And my this slit width is suppose W, is W. Now suppose my exit and entrance slit are equal or identical. Now when my delta y is equal to W, the slit width, then actually we are going to get our this D is going to, this delta lambda is going to be delta effective when our delta y is W or slit width. At that position, that cos R is already 0. So our delta y, the change, maybe you can say that that change will reflect in the the slit width, right? The slit width already W. If we make our delta y or a change, finite change in the that y position in the grating, that they are as W, then your lambda effective is going to be, sorry, the delta lambda is going to be your effective bandwidth. So this is another very important equation we are going to show you. See, so what is so this is actually I have written it wrong. So linear 1 by linear dispersion, right? This is the reciprocal of that. So your D inverse is this. So your delta lambda effective is W into inverse of dw. So this is another important relationship we will going to use in the next numerical problem. So the numerical problem says that a monochromator has a grating with 1000 group per millimeter. The focal length of the mirror that focuses the dispersed light onto the exit slit is 250 millimeter. Calculated, calculate the required slit width in millimeter in order to get a spectral bandwidth of 5 nanometer. That is, wavelength focus on two ends of the slits are separated by 5 nanometer. Consider first order diffraction only. See, so the spectral bandwidth is of 5 nanometer, that is effective bandwidth, right? Because see, it is also written that is the wavelength focused onto the two ends of the slit are separated by 5 nanometer. See, the at two ends of the exit slit are separated actually. So this is in millimeter, but due to this millimeter gap, our lambda is actually going to be in 5 nanometer. That is the effective bandwidth that of the by whatever the light we are getting through, right? Through the exit signal. So our delta lambda effective is 5 nanometer, which is in millimeter scale 5 into 10 to the power minus 6 millimeter. As we have to calculate the required slit width in millimeter, right? What else is given? The focal length is given, f is given, right? What is f? F is focal length, which is 250 millimeter. What else is given? Monochromator has a grating 1000 groups per millimeter. So distance between each groups is 10 to the power minus 3 e, actually 10 to the power 1 millimeter by 10. So this is uh, millimeter. 10 to the minus 3 millimeter distance between each groups, right? So what are the equations we have here? So to relate this, we have one equation that delta lambda effective is W slit width into reciprocal of the linear dispersion, right? And what do we know of linear dispersion from our previous discussion? That it is W into this discussion, this one. The D inverse of D is D by NA. So we'll write that. So that is W into D by NA. And given that n is 1 also, right? Consider the first order diffraction only. So what should be the slit width? The slit width W is delta lambda effective into focal length by D. And now I will put the values 5 into 10 to the power minus 6 millimeters into 250 millimeter divided by the focal length. Not focal length, the distance between each group, that is 10 to the minus 3 millimeter. So I will cut 1 millimeter. So 10 to the minus 3, 10 to the minus 3 and 0. So it will be 1, 2, 5, 0 into 10 to the power minus 3 millimeter, which is 1.25 millimeter. So if we keep the slit width, 1.25 millimeter, and the effective spectral width is to be 5 nanometer. Okay, now this is for suppose the question number A, and what does question number B says? That if the slit width in the monochromator, suppose this slit width 1.25 millimeter, is increased 100 times. Suppose we are solving this question here, another color maybe. Suppose now my change slit width is 100 into W, which has become 125 millimeter. This is my new slit width. So what is going to my delta lambda effective? That is going to be obviously W dash into D by F. We are considering the first order diffraction, so 125 millimeter. D is how much? 10 to the power minus 3 millimeter, and this is 250 millimeter focal length. 1 millimeter we cut. This is 2. It is going to be actually 500 nanometer. Delta lambda effective. So much. So, what is the question? Then, if 100 times an array detector is connected to it, then how many detectors should be there in the array in order to get a resolution of 1 nanometer per detector? So, we will need 500 detectors, right? Detectors in the array to get a resolution of 1 nanometer per detector. These are the few concepts I want to discuss in this uh, session so that you have a better idea. So whenever you are going to use a spectrophotometer or fluorimeter, you are going to see you can change the slit width in nanometer. Don't think the slit width is actually is in nanometer. That is very finite. So that is in millimeter. The change in millimeter is going to change your uh, spectral bandwidth into nanometers. Okay, so the slit width of 2 nanometers doesn't mean the slit width is actually 2 nanometers. It is in some millimeters. So different, uh, different, uh, different grating or different distance between the groups is there in different fluorimeter or absorption spectrophotometer, and depends on that your this relationship is going to be right, that what is the lambda effective and slit width is going to be. So I hope this part is clear to you. Now we have 10 to 12 minutes left. uh, I should I discuss Michelson interferometer in between that, or should I discuss it later? Let us discuss it as we have 15 minutes of time, maybe. Yeah, and we will be able to finish our week one uh, notes, right? Whatever things has been discussed in the first week. So actually, why we need this Michelson interferometer? Because we want to modulate our frequency. Let me use a maybe different color. I'll write it here. Actually, if you see your time domain spectra, so this is the optical frequency. See, the optical wavelengths we are going to deal with is in UV or visible range, which is suppose 350 or 500 or 700 nanometer. So if you check the optical frequency or the time period of uh, each of these wavelengths, suppose I'm going to calculate for 500 nanometer. So for 500 nanometer, what is going to be the lambda is 500, then what is the frequency? Lambda a 1 by lambda is c by a, sorry, c nu, sorry, and nu equals to c by lambda. So lambda equals to c by nu. C is 3 into 10 to the power 8 divided by, suppose this is 10 to the power 8 meter per second. So I have to also convert this in 500 into 10 to the power minus 9. So see, your frequency is coming at 6 into 10 to the power 14. If this is the frequency, then assume what is going to be the time period. So that time is coming as 1.6 into 10 to the power minus 15. So that is femtoseconds. Did I made any mistake? I hope not. So this is coming in femtosecond, or even so our oscillator can't really work in that frequency region, right? So we want some instrument or some mechanism so that we can modulate this
optical frequency into uh, some frequency range which we can use in an oscilloscope or uh, somewhere. So we want to modulate this. So that is why we are going to use this scheme that Michelson interferometer. What is it is actually doing? See, so there is a source of light. Okay, from where a monochromatic for the time being we are discussing. Suppose start with a monochromatic light is being produced and it is fall onto this mirror which is collimating the beam and it is falling into a 50-50 beam splitter. So what is happening that some part of the light in these 2 points 50% is reflected and 50% is transmitted. Now in this side there is a fixed mirror and this side suppose at zero position there is a movable mirror. So movable mirror we can move and what will happen that 50% is transmitted and 50% is fixed is reflected, then that is again coming back. So so 50% of this reflected light is transmitted and 50% again coming back to the source, and 50% whatever is going to this transmitted light earlier, that is going to reflected from the movable mirror. 50% will be reflected and 50% will be transmitted again to the source. So this half is going to come to your sample, and from that sample it will eventually come to the detector. See, if so this is a movable mirror which I can move. So it is shown that if the movable mirror can be moved to plus minus lambda by 2. Lambda is the wavelength. Okay. So when suppose both are fixed, then you are going to get a constructive interference, right? When this is fixed and the movable mirror is positioned at 0. So then you are going to get a constructive interference. Now suppose your mirror is moved to B or C position, which is at minus lambda by 2 or plus lambda by 2. So you will see your this transmitted light or this light is actually going to, to move by lambda distance, right? If I am moving my mirror by lambda by 2, then my uh, gap is going to be, or you can say it is going to lambda by 2 to, and again lambda by 2, because it will go and will come, right? So it will be the path length will be changed by lambda if I move my mirror by lambda by 2. Similarly, if I move my mirror by lambda by 4, then the distance is going to be the change in the path length. Suppose I'm going to write it, which is suppose delta or retardation. This is also known as retardation, which is actually the distance into 2 into m minus a. Suppose when I'm going to move and this is my what is going to be retardation or delta. Suppose I move my a by plus minus lambda by 4, then my retardation will be plus minus lambda by 2, right? When I move my mirror by plus minus lambda by 2, my retardation would be plus minus lambda. So at this position, lambda by 2 position, I will going to get a detector. So it will fall onto the sample, and when the distance is retardation is lambda by 2, I am going to get destructive
interference, and when my distance is by, so here there, when there a gap of lambda is in half integer, then and the phase are different. Uh, Phase are exactly opposite, and when it is different in zero or maybe positive integer, or sorry, in positive or negative, just an integer, not a half integer, then I am going to get a constructive interference. Okay. Depending on that, if we see the y-axis is power and x-axis is delta retardation, you can see you can get a beautiful cosine curve. Where at zero, you are going to get intense light, right? Because of the constructive interference. Then again, when you move to lambda by 2, retardation is lambda by 2, you are going to get a destructive interference, 0. Then again at lambda, you are going to get, when you move your mirror to lambda by 2 position. So to get delta, so this is a full cycle, right? So get a full cycle or a full wavelength, my delta retardation is lambda, and I have to move my mirror lambda by 2, right? Lambda by 2 distance. As I am going to positive direction, you can also think about the negative, right? Lambda by 2 distance. Suppose, so for a full cycle, so suppose my frequency, I'm saying the frequency of this interferometer is f. Okay, so f is going to be 1 by this time period tau. Tau is the time taken to move the mirror to lambda by 2 distance. Tau is the time taken to move mirror to lambda by 2 distance, right? And also, suppose my uh, mirror is moving with constant velocity Vm, V capital M. So I can write, so I need a blank page maybe. So, so tau is the time and Vm is the velocity. Then this is my lambda by 2, the distance, right? So tau is nothing but uh, lambda by 2 Vm. Now frequency, which is f, frequency of interferometer, 1 by tau, which is 2 Vm by lambda, and lambda is the wavelength, and we know that your frequency, that is optical frequency, nu is c by lambda. So your lambda is equals to C by nu. So if I replace this, M by 2 Vm mu by C. So this is my relationship between, I can see that this using this Michelson interferometer problem, I can modulate my optical frequency. I will modulate this optical frequency to this interferometer frequency, which is going to be smaller than the, and it will mostly come into the audio range, some thousand of hertz or maybe less than, and which we will work to do with the Fourier transformation, right? This has been taught, I think, is in the class, right? So this is Fourier transformation is used to from time domain to reach frequency domain or vice versa. I'll just show you a example in the next slide, and we'll finish by that. That as you can see that if you have a monochromatic light in the frequency domain, this is the frequency domain, you have a monochromatic or single frequency, then you are going to be have a very commonly a cosine wave with a single frequency, right? And it will look like this. Uh, in the interferometer, right? And the interference pattern will be like this. But when you are going to have two different frequencies with two different amplitudes, you are actually going to get your the interferogram will look like this. It is getting complex, right? And obviously the your interference pattern will be different. See, actually, when we work in our frequency, I told you we generally got a broadband, something like that. So actually, we got get a emission or absorbance by band like this. So when we are trying to look, so this is the frequency domain. So this can be captured in the time domain within a second using uh, this Fourier. So this time domain measurement. This is the time domain measurement, and as you can see, this looks like this. Why? Because there are multiple frequencies are there, okay, and they are interacting. The frequencies or the wavelengths are interacting. So at some point, it is creating a destructive, and at some point, it is creating a constructive interference, due to which your pattern interferogram patterns looks like this. And using the FTIR, you can always travel between time domain to frequency domain. Oh yeah, and the what is the advantage of time domain? I guess already he taught by a professor and Datta. So I'll not go deep into that, but this is what I wanted to show you. And with this, I hope you get a much better idea at the monochromators, what is actually happening at the gratings and all. And tomorrow means the next session, we will try to solve some more numerical problems on the quantum fields, and maybe on these monochromator problems, and maybe something on the Michelson interferometer. We'll try to solve some problem, and obviously we'll discuss the week two lecture notes or lecture videos. With that, today I'm going to end this. I hope you are going to listen this thing in the YouTube, and this has been productive to you. With that, I am ending today's session. Hope to meet you on the next week. Thank you.